look at something called a composite function. A composition of a function, or composite functions, if you will. So let's start with a definition. What is a composite function? It's a composition, as it will be, of two functions. Here's our definition. The composition of two functions, say f and g, functions, we'll call them f of x and g of x, is defined by the following relationship. As, and we write it this way, we use parentheses, and f, and we put a little open circle. That's the composition symbol. F composed with g, and then you write it of x, which actually means the following. That actually means this. This is the way we're going to reference it sometimes. I prefer this other notation because it means f of g of x. So we put the second function as an input into the first function. And this is, both the left-hand side is read as f composed with g of x. The second one, that is simply read as f of g of x. So that's our definition. Let's work with it. It looks kind of strange. We're putting a function into another function, so it gets a little bit awkward looking. Let's take a look at some simple examples of the composition. So we need two functions, f of x, and let's define that as something, make it simple, 2x plus 1, and let's take our g of x to be x squared minus 1. So let's use this definition and compute our composite function. We're going to do it both ways. We're going to do f composed with g and g composed with f. Of course, you can switch it around, call f g and g f, and you still have a composition. So we're just going to follow the rules and then see where it leads us. So let's compute the composition first. F composed with g of x. And again, it's f of g of x. So if we know what we just did, I can start with my function f, and what I'm doing is I'm putting in g into the argument. So this is equivalent to my f, my function f, is 2 times my input plus 1. That's my function f. That's a functional form of it. What I'm inserting into the argument is just x squared minus 1. Because I'm putting g into the argument. So then I simplify this, it just becomes 2x squared minus 2 plus 1, so it's simply 2x squared minus 1. So it is. Evaluating one function, its argument with the other function. Try this one. Say I wanted to swap it around. So I want to compute g composed with f of x. See if you can do that yourself. The same function, f and g. And see what you get for that one. Hopefully, after you multiply everything out, you should get, something like that. Wait, 2, 4x. Right. Do it in my head to make sure I did it correctly. Does anyone want to see how I got that? Just chime in. Okay, let's kind of do how we got that. Same f and g, but now instead of f composed with g, we're now doing g composed with f. So I'm going to be doing g composed with f of x, which is g of f of x. So my functional form of g now is my input squared minus 1. What is my input? Well, my input now is the entire function f of x, which is 2x plus 1. So what do? I simply square this out, FOIL it out if you will. So I get 2x times 2x is 4x squared plus a 2x plus another 2x plus 1 minus 1. Well, they cancel out over here, and I just add the two x's together, the like terms, 4x squared plus 4x. All it is. Okay, let me give you one to try over here. Let's see how well you guys can do on this. I want both of them. Try the following. So let's define our f of x is the so compute two different things. And one thing I want you to compute is f composed with g of x, as well as g composed with f of x. Try those. See if you can work through the algebra on those, and I'll work through it in my head over here and see what we come up with. Now we're going to assume that x, is positive. So make the assumption, make life easier. We'll assume x is greater than or equal to 0. It's not negative, so we don't have to worry about anything into the radical. Actually, you can actually assume it's greater than 2, but. Does anyone want to see how I got that? Anyone want to see how I got both of those? Is it okay? Okay, so let's plug it in. Let's do the first one over here. Again, the way I like to do it is take f of g of x. Okay, so what is my f? Well, here's my function f. It's the square root of an input minus 2. I put the functional form of f first. And what is the input? Well, the input is the entire function g of x. So that is just simply x squared plus 2. Well, I can simplify what's under the radical there. Is that just plus 2 minus 2, so it's the square root of x squared, which is x, provided x is greater than or equal to 0. I don't have to worry about absolute value symbols. That's all it is. Let's take a look at this one, which is just the opposite. Now this is g of f of x. So I start with the functional form of my function g, which is take the input, square it, add 2. But what is my input? Well, it's my entire function, f of x, which is the square root of x minus 2. Well, what happens when I square a radical? When I square a radical, the radical symbol vanishes. So this becomes nothing more than x minus 2, and then I had my plus 2 that was already there, so that gives me again x. Everyone kind of see that? Now, interestingly enough, there's a relationship between these two functions. We'll explore that more on tomorrow, but let's take a look at the graphs of those two functions using Desmos. I haven't set it up yet, but let me just kind of set it up. We'll get that running. I'll come to the onboard calculator. Let me get you guys over to that. So here's our Desmos. Let's take a look at those two functions, f of x. So I'm just going to call that y is equal to the square root of x minus 2. Well, there's that function. Hopefully you can kind of see what the domain of that function is. Remember, all x has to be greater than or equal to 2. And the range goes from 0 up to infinity. Let's take a look at the other function. Y equal to x squared plus 2. Take a look at that function. And let's just throw in, for the sake of it, y equal to x. And you might notice a little bit of the something here. If I ignore the green graph to the left of x equal to 0 and just have this portion over here, and if I rotate it about the line y equal to x, I will get the blue graph. They are inverse functions of each other, provided we choose the domains and range appropriately. We kind of restrict the domain over here to just have x being greater than or equal to 0, and here the domain is x is greater than or equal to 1. We don't need to restrict it, but we do if we want the inverse of that. That's always going to happen. Let me just point this out. We will discover this more tomorrow, but this requirement of getting an x out here and an x out here mean these two functions are inverse functions of each other. That's what we're going to show tomorrow and kind of talk about that. But it makes sense. The idea of an inverse function, it takes you to where you start. For example, you know, the square and square root functions. I'm going to work some more of these. So now let's just kind of take it aside on this. And a little idea, because tomorrow it's a shorter day, but it's a complicated day. And that's why I don't want to overwhelm it. And that's our last topic. But we know that inverse functions take us back to where we started. For example, if I have the function x, and then I use the squaring function, which is takes that x and square it, then its inverse function would be, all I do is I take the square root of x squared, and again here x has to be non-negative. That'll take me back to x. So here's my kind of like my f of x, and here's my f inverse of x. And it should go back the other way. Because if I come here, I can go from here, to here, back to where I started. So it should run both ways. That's why you need to do f composed with g and g composed with f. That's what we're going to focus a little bit on tomorrow. This is going to be our test, our algebraic way. If you don't have any graphical device to use, this is an algebraic way of testing to see if two functions are inverses of each other, with their domains suitably chosen. You might have to restrict the domains, as we're seeing from the last graph there, to make that work. Okay, but let's get back to these composite functions and give you a few more to try. We will talk about that in greater detail tomorrow, and that's the last topic we will consider. And then we'll kind of give you a review of everything that we need for our test on Thursday. And Thursday, you'll go right into taking the test at class time. You'll have time to take it then. Now let me give you a couple more to try. Some of them, most of them are not inverse functions, so you can just see by looking at the graph. There's a select few that satisfy this inverse function idea. So try some of these. That one, and I want you to find both, f composed with g of x as well as g composed with f of x. Now sometimes you don't write the x dependence, sometimes you'll see it like this. I'll include it most of the time, but it's not always there. The x dependence may or may not be written. Give you another one over here and see how well you can do for these. Practice your algebra. I'll give you two to start with. And we'll see how well we do. Now I've got some other examples in the textbook, so you can kind of use those. I'm going to try some other ones here in a moment. These are just rational functions. We're going to look at some non-rational functions. Because I do it in my head, so I can easily make a mistake when I do the algebra in my head. But. Anyone want to see how I did problem 1 there? I don't want to see how I did problem 1. What about problem number 2? Any questions on problem 2? Do both of them. This is an easy one. We'll do both though. Okay, so this is nothing more than f of g of x. Well, what is my functional form of f? That's 1 over my input x. But what is my input now? It's 1 over x minus 2. So this is equivalent to 1 divided by 1 over x minus 2, which is equivalent to 1 times the reciprocal of that. So it just gives me x minus 2, exactly what I have here. So that's not too bad. Let's take a look at the other version, g composed with f. It's a little more complicated, a little more challenging, especially when you want to do the algebra to simplify it. So that is equivalent to g of f of x. That's another way of writing it. So I look by functional dependence of g, it's 1 over my input minus 2. But the input now is the entire function f of x, which is 1 over x. And what do I have? I have 1 divided by 1 over x minus 2. There's a couple of ways of simplifying this thing. And the easiest way is I want to clear out that x here, so I multiply the numerator and denominator both by x. I multiply that by x and that by x. You'll see nice, easy simplification. So in the top, 1 times x just gives me x. In the bottom, x times x over 1 just gives me 1. Minus 2 times x gives me minus 2x. That's exactly what I have there. Very simple way. Now, what can we say? These functions are not inverse functions of each other. We'll talk about that tomorrow, but they're not. Okay, let me give you another couple to try. This is work some of the algebra. We're going to kind of work some of the algebra so we understand how to do this and how to do this effectively. Now I'm going to move away from rational functions, and let's just start looking at some of our other types of functions. We looked at polynomials, we looked at the radicals. Let's take a look at exponentials and logs. So here's another set of functions we want to try for. So f of x is, say, the natural log of x, and let's make it a simple one. G of x is equal to easy x. Make it x, let's leave it as easy x. And try this other one. We'll do the exponentials again. F of x is, say, 2 to the x plus 1. And g of x is a log in the base 2 of x minus 1. So try those two and see what you get for each of those compositions, f composed with g and g of x. So each of them is f composed with g and g composed with f. Those are, as we know, inverse functions, so they do undo each other in that specific way. That's just like that. Try to simplify it. I'm not going to give us much of a simplification. We can't crack that nut. Those are not inverse functions of each other. So let's start with 1. Does anyone want to see how I did problem 1? Okay, let's kind of go through that. This is my composition over here. Let's start with the first one, f of g of x. So here's my function. F is natural log of the input. What am I putting in for g? I'm putting in e to the x. These are defined to be inverse functions of each other. They cancel each other out. The natural log of the exponential just gives me the input. Flipping it the other way, I have my g is e to some input. Well, my input now is the natural log of x. They are also inverse functions of each other, so they cancel out. Just like taking the square of a square root and the square root of a square, both of them give me back to x. These are the properties of the logs and the exponentials, provided they're the same base over here. Since you had a question with that one, let me go through this one as well. Let's do this one first. So f is 2 times my input plus 1. So my functional form is 2. I'll make it black. I'll put the input in blue. So it's 2 times the input, my x value, plus 1. But what is my input? It's the log in the base 2 of x minus 1. Make a little extra space over there so I can put it in there. Here we have the log in the base 2 of x minus 1. Now, I can't cancel this directly. What I need to do is rewrite this. So here's, I can rewrite that as the following. This is equivalent to 2 times the log in the base 2 of x minus 1 times 2 to the 1. Remember, we have the same base, you add the exponent. So that and that are equivalent. Well, that just means there's a factor of 2 that's out front of this. There's 2 times 2 log in the base 2 of x minus 1. They're inverse functions of each other, so they cancel, so it gives me 2 times these cancel to just give me x minus 1. That's what I had, 2 times x minus 1. Now the other, g composed with f, there's not much you can do there. Let's just put it out and we'll see. So now we're going to do the opposite, which is g composed with f. So now my functional form of g is x log 2 and put in my input and then subtract 1. Well, what is my input now? It's 2 to the x plus 1. There's nothing I can do. I can't, I could bring it down this and write that it's 2 times 2x, but it's not going to give me anything that'll simplify. So I'm pretty much done here. I can't do anything. I'm pretty much done with the water. 2, the x plus 1 minus 1 down here. That's it. Nothing else you can do. I can't do it. We're going to find some other properties of logs later on when we'll show how to work with these. Okay, let's just close out with some trait functions and their inverse functions. Just kind of see how that goes. And you can mix them all up in many different ways, shapes, or forms. But you just have to practice. The more practice you do, the better you get at using and performing the algebra. It's going to be a major tool throughout this course and calculus. So try another set of these. That one and try another one. Make it a simple one. You can mix it up in many different ways over here. So put the two things we're looking for, the compositions of both ways. Now, I'm not defining the functions, giving their domains and ranges. Technically, you really have to do that to make this work out, to make sure that the x's we're putting in and taking out are correct. So we're kind of being fast and loose with the facts over here a little bit. But just to get you through the basics of this, we're doing it this way. We really have to be very, very precise over here. We're being imprecise, and I'm doing it for a reason, so as not to confuse anything. But just so you know, we know that the aux sign can only have x of a certain type. Its input has to be in a certain range, a certain domain, I should say. Anyone want to see how I did problem 1 over here? So I'm going to see that pattern. We're finding functions and their inverses. They cancel each other out. Anyone want me to show you problem 1? It seems to be okay. And let's go through it. So for the first one here, this is F composed with G. That's equal to F of G of X. Well, F is my sine of my input. My input is the entire function g of x, which is the inverse sine of x. Well, what happens here? They cancel each other out. It's like taking the square of a square root of a square root of a square. So that cancels out to just give me x. Similarly over here, this is g of f of x. Well, g is my arc sine of my input. Now my input is my sine function. The arc sine of the sine cancels out to just give me x. All of this. What about this one, problem 2? Anyone want to see how to do problem 2? Think they have this understanding? Have to get used to how these functions work. So we're okay with this? Everything's okay? Okay. So you kind of see how this composition works. But this is where we're really going to be using it. We're going to be using it to test if two pairs of functions are actually inverse functions of each other. But it's actually used in other things later on. This is a fundamental thing that you'll look at when you look at some more complicated things. If you go on and go into graduate school or even engineering courses, when you look at different things, they'll be doing transform methods and compositions and things like that. So this is a skill that you will need later on. It's a strange looking thing. It just looks a little bit different, but it's something you need to do. Just try one last set, something similar to the homework. I'm making these up as I go along in my head. Yeah. Try this one. This is slightly different. Very simple. This is an easy one, but see if we can do this correctly. Try that. Try to do the compositions of those two functions. F composed with G and G composed with F. Notice I'm not writing the explicit functional dependence. It's a shorthand way of writing it. Math is a science of laziness, so. We'll do more of this tomorrow. We're going to do it more in the context of what we're talking about being inverse function. Again, this involves fractions, so a lot of you will have difficulty with your algebra when it comes to fractions. Does anyone want to see how I obtain both of those? Okay, let's start with this first one. This is f of g of x. So I'm going to do it the long way. This is computing f of g of x. Well, what is my f? Well, it's 2 minus 3 times my input. My input in that entire function g, which is 2 subtracting x over 3. So I plugged in g into the input of f. Now what can I do? Let's simplify this. I can distribute the 3, that'll cancel. So it'll give me, these cancel right out here. So it gives me 2 subtracting x. Now let's distribute the negative sign there. So I get 2 subtracting 2, subtracting a negative x just gives me x. 2 minus 2 is 0, so it just gives me x. This is flipped around. Now I do g of f of x. So what is my function g? Well, it's 2 minus my input over 3. Well, what's my input? 2 minus 3x. Okay, let's simplify this. Distribute the negative sign there. So it's 2 minus 2, negative gives me a plus 3x all over 3. Well, these two cancel out. And I get 3x over 3, so they also cancel out to again just give me back to x. Now let's validate what I've been saying. Let's take a look at those two lines. Those two functions. Those are straight lines. Take a look at those in, say, Desmos. We can just kind of see what's happening over here. We'll go back to Desmos over here. I'll put one function there as 2 subtracting 3x. And this other function over here, which is just 2 minus x divided by 3. And there's the line. The purple line is y equal to x. Notice if I flip the blue line, about that line y equal to x, it turns into the green line. So those are inverse functions of each other. They undo each other. The argument of one and put into the argument of the other gets you back to where you started. Kind of seeing what we're leading into tomorrow. Any questions? So this is good. You got to practice algebraic manipulation. These skills need to be fine-tuned before you attempt the calculus. If you go in calculus with weak algebra skills,